We turn now to collaborative filtering, beginning with the user-user version. In collaborative filtering, instead of using the content features of items to determine what to recommend, we're going to find similar users and recommend items that they like. Let's see the user-user version of collaborative filtering. Consider we have user X and we have some item I they haven't rated. Let's say we've learned something about user X's preferences on other items. Now we find a set of n other users whose ratings are similar to X's ratings. And now we estimate X's unknown ratings, like the ratings for I, based on the ratings of the users in N. So we'll need to find similar users and recommend items they like. To find similar users, we'll represent them by their rows in the utility matrix and say that they're similar if their vectors are similar. So perhaps users A and B are similar because they both love Harry Potter 1. And maybe A and C, we'd like them to be dissimilar. A loves Twilight, C loves Star Wars, but they both hate the opposite one. Okay, let's turn those ratings into vectors. Suppose two users have the following star values for 5 items. User X has 1 star for item 1 and 3 stars for item 5 and so on, and no ratings for items 2 and 3. Let's for the moment represent a blank rating by a 0. Now we can just compute the similarity with cosine. We know how to do that. But this representation has a problem leading to unintuitive results. Consider our utility matrix again. We'd intuitively like A to be much more like B and very different than C. A and C had exactly opposite opinions. But cosine doesn't treat that 1 as a negative rating, and it doesn't properly treat a lack of rating as uninformative. It treats a 0 as very close to 1. So we'd like similarity of AB to be much greater than similarity of AC, but in fact, if we compute the cosines, the similarities are very similar. Yes, A is a little more similar to B than to C, but only a little. The problem with cosine is that it doesn't really capture how opposite A is from C. And another problem is we'd like to normalize for raters. For example, rater D rates everything the same. Their ratings are not informative. We'd like a way to treat the zeros as uninformative, the low numbers as negative ratings, and people who like everything the same as not helpful. The solution is to mean center the users, subtracting the means from each row. So this row, we add it up, 4 plus 5 plus 1 over 3. That's 10/3 or 3 1/3. If we subtract 3 1/3 from 4, we get 2/3. So, and from 5, we get 5/3 and so on. So for each row, we compute its mean and then subtract it from every element. We don't subtract from the null values, and we leave them as 0 in the end. Now, a 0 means no information. Zeros can happen because we have no rating at all, or because the rater is uninformative. Notice that rater D rated everything the same, and now D's opinions about these movies is no longer informative. Now, a very low rating has become negative, and opposite opinions are reflected in vectors that have opposite signs and will point in different directions. This kind of mean centering is useful in many problems in processing natural language and data whenever we have a scale like rating or sentiment that intuitively has both positive and negative ends, and when we have values with no ratings. Now, if we compute the cosine in the mean-centered utility matrix, notice that A and C have opposite values, and their vectors are very, very different. Indeed, their cosine is negative. A quick terminological note, subtracting the mean is mean centering, not normalizing. Normalizing is dividing by a norm to turn something into a probability. But the textbook and common usage sometimes overloads the term normalized, so you'll sometimes see this called normalization. All right, let's see the final modified version of cosine we're going to use. We're going to make one more change. So we have our vectors of user ratings. And for each user, we compute the mean, ignoring missing values. So the mean for Rx is 1 plus 1 plus 3 over 3, or 5/3. And it turns out to be the same for user Y. Then we subtract this average from each of their ratings, doing nothing to the missing values. The missing values stay null. So now mean centering user X, we get 1 minus 5/3. That's negative 2/3, and so on. We don't change the zeros. Now we're going to add one more change. We're only going to keep items that both users rate. So here we're going to remove these 3 items that weren't rated by both users, get 2 shorter vectors, and take the cosine between these shorter vectors. In summary, here's the mean-centered overlapping item cosine similarity algorithm for user-user similarity. Instead of the basic cosine similarity between user X and user Y, the mean-centered overlapping item cosine similarity, we only look at items rated by both users X and Y. And for every such item, we subtract out the mean for each user and now take the mean-centered overlapping item cosine. It turns out, by the way, that mean-centered overlapping item cosine similarity is a slight variant of the Pearson correlation. Now that we have a similarity function, we can see how to make recommendations for some unrated item I. Let R sub X be the vector of user X's rating, and N be the set of K users most similar to X who've rated item I. The prediction for item I of user X, we could just say, take the mean of what the K people like me rated. So we take the K users in N, and for each user Y, we take that user's rating for this missing item I, and we just average them. That's our predicted rating that X would give to I. Even better, we could rate I as that same mean, but weighted by those other users' similarity to me. So our estimate of X's opinion about I is the sum over the similar neighbors of their opinion about I, weighted by how similar they are to X, and divided by the sum of those similarities to normalize. We've now seen the user-user version of collaborative filtering.